I see the recording has started, and I see the clock is showing 1 o'clock UK, which is 3 o'clock Lviv. So shall we get going? Welcome everyone to the second day of the 2026 Ising Lectures, 28th Annual Workshop on Critical Phenomena and Complex Systems. I'm very grateful to the organisers for inviting me to chair, or co-chair, I should say, this day. We have 3 lectures from 2 lecturers. So Jan Korbel will be giving the 3 o'clock and the 4 o'clock lectures, which are 2 parts of Foundations of Entropy in Complex Systems, and then Ferenc Gloi will be giving the first part of Disorder and Order in Quantum Systems before we close for the day. The schedule says we stop each at 10 minutes to the hour. We will try to stick to that so that people can take screen breaks and make coffees and so on. And I will give Jan a little warning at 1/4 to the hour to try and make sure we come in on time. I don't know what the convention is about questions. Jan, I suppose you can decide really whether you'd like them at the end or during or both.
I will probably follow what is common during the lectures. I don't know, Yuri, what is the...
So we had different ways of putting questions. Sometimes raising hand during your talk and sometimes afterwards.
So I'm happy to answer the questions immediately. If this goes too much of the track that we spend too much time on first 3 slides, then let me know and we adjust it. But yeah, and basically, since I will be trying to look at the other participants, but you can just unmute yourself and just straight ask the question, because I will not be probably taking much attention to the raising hands and these things. So just,
and of course I will also keep an eye on the participant list, so if someone has their hand up and hasn't been noticed,
sure.
I could also intervene on their behalf.
Thank you.
Excellent. With these housekeeping matters out of the way, it's my great pleasure to introduce Jan Korbel from the Complexity Science Hub in Vienna, Austria, who will be talking to us about foundations of entropy in complex systems. Please take it away.
Thank you very much. First of all, I would like to thank the organizers, Yurko and Oksana and others, for having me, because I really have been enjoying these lectures. There have been great speakers, great talks, and it's a pleasure for me to be part of this series of the workshops. In this talk, what I would like to do is that I would really like to start from of how to go to the roots of what is entropy and what is the entropy, especially in complex systems. So let me start with the classical quote from the book by David Kolst, that Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest died similarly in 1993, and now it's our turn to study statistical mechanics. So, of course, it's kind of dangerous to study statistical mechanics, although this sample is quite small, maybe. But I think that these people, especially Ludwig Boltzmann, have done really great job in discovering what the statistical mechanics is for the case of that has been discussed 1 century later, which is complex systems. And this is basically the aim of this task. The lecture is to show you how the results of Ludwig Boltzmann can be applied to complex systems. So let me start with introducing my institute. It's called Complex Hub. We are in Vienna. We moved last year to we were in nice palace, but we are now moving really nice palace. It's called Palais Rothschild. It's near Belvedere. It's very nice palace that has some historical saloons. So everybody who is coming through Vienna, just let me know, drop me a message, and we are happy to have you as visitors and maybe have some discussions, talks, etc. Why I'm mentioning it was Vienna is a city of famous people, and if people come to Vienna, some of them are also trying to see the graves of these famous peoples. Most of the people, there is like a big part of the central cemetery, where it is called Ehrengraben in German, where you have this like famous people buried in a special section of the cemetery, and people go and see graves like Beethoven's graves and other composers. Maybe some others go to like more popular composers like Udo Jürgens, who is like has been very popular here in Austria. And then there is a second class of people who are physicists, and they typically go to this grave. So this is a grave of Ludwig Boltzmann, and on his gravestone he has this formula: S is equal to K log W. And what is the aim of this talk is to show you how important the Boltzmann's formula is for statistical physics of complex systems, because everybody here probably had a course on statistical mechanics where we learned this, but then later we were like, okay, so we know this, but then there is this powerful thing called Shannon entropy, and this is something the Boltzmann is maybe some simple version, special version of this Shannon entropy. I will show you in my lecture that it's the other way around. This is really the most fundamental quantity, I believe, in the whole statistical physics, and this is how you can connect the microscopic with mesoscopic and macroscopic. So let's go to discover how we can make use of this in complex systems. So and before I start, I have to say I really wanted to start from the very beginning. Most of the people probably will find it kind of basic or introductory, but I really wanted to start from the beginning because also historically there have been some misconception about what the entropy is, how it's used, etc. And I think by showing these simple examples and going from the very beginnings, building up the theory, and then showing how it can be used beyond the traditional application statistical physics makes a lot of sense. Also, if there are some students who are not that familiar with statistical physics, it's also helpful for them. Okay, so the way how typically we start in statistical physics is that we say in most physical disciplines, we are interested in detailed description of physical systems. So basically, it means that we take one particle and we study its evolution. And if it's classical particle, then we study its classical trajectory. If it's quantum particle, we study how the wave function evolves. If it's electromagnetic field, then we study how the field evolves. And in physics, these independent quantities are called degrees of freedom. So it's like particle position, particle velocity, molecular angular momentum, etc., etc., etc. And for each degree of freedom, we have typically, can be different, but typically we have one differential equation that is interconnected with the other degrees of freedom. If it's sometimes, if it's very simple, they are not interconnected, then we can solve as many as we want. But if they are interconnected, then we have to solve all these equations together. And now the question is, what happens if we have one more of these particles, so roughly 10 to 23, and that's where the statistical physics come into the game. And so typically how we start is that we start with Liouville theorem, where we say we have canonical coordinates which describe generalized position and generalized momentum, and they depend on some Hamiltonian that describes the energy of the system. And then we say that basically the probability distribution in phase space satisfies this Liouville equation. As a consequence, if we write this functional, that is somehow we know that now it's entropy, then the entropy doesn't change in time and remains constant. Good. But what happens if we are not able or cannot or don't want to take into account all of these possible degrees of freedom of all that are involved in the dynamics of our system? Before that, I quickly mention some results that we will be using: law of large numbers, central limit theorem, where we will be using this to basically decrease the number of degrees of freedom, because we will be going from this detailed description to some aggregated description. Also, what is very useful, particularly useful, I just have this quick reminder is this bars and stars theorem is basically how you calculate the combinatorics combinations with repetition. So this is something that it will be useful in this lecture. Okay, so now the emergence of statistical physics, how it emerges is really through this coarse graining, which means that what we do is that we look at the microscopic system and decide maybe not every degree of freedom has the same importance, or we are not actually interested in that. We are interested in some macroscopic properties that give us the overall macroscopic description of the system. So this is like the typical picture where you start from quantum, atomic physics, some chemistry, and then some biochemistry, and you can go as to other higher scales if you want. And how this is done is that it's basically you are coarse graining, and you are basically compactifying the degrees of freedom from many to a few. So something like if you take this six dices and you throw them all, you calculate the average value. And this is basically what is the most important concept in statistical physics. Let me quickly just remind ourselves what is the difference between microstate, mesostate, and macrostate, because this will allow us to basically distinguish between these three and then help us understand what is the consequence or what is the interpretation of Boltzmann's entropy. So if we stick with the example of basically dices, we have a dice that has 6 states, that is regular dice, that is not biased. Basically, every side can appear with the same probability. Good. So now we throw a dice 5 times, and now the resulting sequence, basically, so we say the first dice is 4, second is 4, 6, 2, 5, is a microstate. If we consider this specific system, the number of microstates is basically 6 to 5, which is this number. So it's 7,776. Now what we can calculate is the histogram. So how many times we see which number. So here 1 is 0 times, 2 is 2 times, 3 is 0 times, 4, 5, and 6 we see once. And now the number of mesostates is much smaller. Number of all possible mesostates is this combination number. It's again because we have the combination of repetition, 252. And now we can ask again what is the average value that we observe. In this case, if we basically calculate what is the sum of them and divide it by 5, this is 3.8. And then we see that the number of possible macrostates is 25. And since this is an example of relatively small system, we still see that in each step we go 1 order of magnitude lower. In larger systems, it means that we go many orders of magnitudes lower. If we consider the space as a number of all microstates, number of all mesostates or macrostates. Good. So now we have the multiplicity. And the multiplicity, this is what appears as W in Boltzmann's formula, is simply the number of microstates with the same mesostates or macrostate. So it means that now we come back to the formula on Boltzmann's graph, and the question is how we calculate the multiplicity. So for this case, it is easy because we know that basically the trials are independent. So we go back to our high school class on combinatorics, and we know that is a combination number. And what we do is that we basically say we permute all the states, so basically do all the permutations, but we have to take care of overcounting, because like if we have this 2, then if we swap the same states, it's not actually a new state, it's basically the same state. So here the question is how if we have the mesostate that contains 2 twice, 4, 5, 6 once, then basically the number of these, the multiplicity is 5 factorial over 2 factorial, which is 60. I'm now introducing this this sequence as a representation of the histogram. So this is just how to represent a given histogram. Okay, so this is what we know very well. And of course, this is what we also know very well from our statistical physics lecture. If we then plug into the Boltzmann's formula, so we take the logarithm of the W, then basically it means that we get n log n minus n. This is because we use the Stirling's approximation, where logarithm of x factorial is x log x minus x. We do this. We use the normalization because we know that the total number of trials is n, and then we introduce something that could be called probabilities, which is just the number ni over n. We get the famous Boltzmann-Gibbs-Shannon entropy formula, as you want. I'm now setting aside the Boltzmann's constant. I set it to 1, but of course this is the thing that connects the information with thermodynamics, because it says the units that then translate this that is dimensionless to the Boltzmann per Kelvin right units. Good. So this is basically, we ended with the formula that's known as Shannon entropy. So basically the Boltzmann-Gibbs-Shannon entropy can be derived as a direct consequences of Boltzmann entropy if the multiplicity has this form of multinomial factor. And this is well known, and it is used everywhere, not in physics, it's used in statistics, in all sciences. Okay. Now, one thing that we need to address is that what is actually a PI. I just introduced the PI as this ni over n because we use this law of large numbers, where we say for large n, the relative frequency of an event converges to its probability. So that's why I called it probability, even though it's more like relative frequency. So now it means that in this case, if we have this, and we said, okay, so before any information, our prior probability was uniform, was 1/6. If we now consider this, so take this histogram, and we say, what is the probability of seeing 2 in this when we follow this histogram? It's not 1/6, it's rather 1/3. So with the new information, we update our probabilities. And then, of course, sorry if there is a typo. So what we do is that we can make use of this entropy to infer new the probability distribution based on the available information. So now we can ask, so now we have the same example, 5 dice, but now what we say, we observe that the average value is 3.8. So it means that the total sum is 19. And now we can ask, what is the mesostate that corresponds to this measure? And there are like many possible mesostates, right? This is the one that we saw. There's another one where we have 0 ones, 2, 3, 4, 2 times 5, and 0 times 6. And there are like also mesostates where we have 4 times 4 plus 1 times 3, etc., etc.
Sorry, Jan, may I briefly ask about the previous slide? How did you get that 1/3? There are 5 dice and 2 of them are 2.
Sorry, 2/5. Yeah.
Right. Yeah. 2 and 5. Yeah. Good.
Sure. Yeah. That's a typo. Right. Good. Thank you. Yeah. Okay. So basically, it means that what we can do is that if we say now what are all the possible mesostates, then of course the calculation is a bit more complicated, because the theorem doesn't care that the maximum value on a dice is 6, so we have to exclude the cases that do not correspond to our example. But we can do this by inclusion-exclusion principle, when we exclude unwanted cases. So after some algebra that is straightforward, then basically we derive that there are 17 possible distinct mesostates that follow this property. So basically it means that there are 17 possible mesostates that have the same average, 3.8. Okay, let me again say that I introduce this notation where I say that 6, 5, 4, 2, 2. So I basically order them from the highest. So say I see once 6, once 5, once 4, and then 2 2s. This is how to take care of this multiple permutations of the same states. So if I introduce this notation, I can show you all of the possible states. They look like this. And now the question is, what is the possibility of observing such a state? So what one would have to do is that one would have to calculate the multiplicity, right? So use the formula, and then we see that here in this case, the W, the largest is this when we don't have any repetition of numbers. So 6, 5, 4. Lowest is this 4, 4, 4, 4, 3 because there is actually many permutations give us the same state. Okay, and now we can ask what happens with the probability. So basically now it's the probability of a state with a constraint. So how do we calculate which probability is observing the value? For example, what is the probability that we observe that we observe 3? Is that we look at this sequence and see how many times we see 3 in this series. So this is once, this is 0, blah, etc., etc. So here this is the probability that we see, basically the highest probability where we see 3. So that we have the basically 2 5s and 3 times 3. And this probability is simply weighted average of probabilities for each mesostate weighted by its multiplicity. So then basically if we say, so over all of these, we can calculate the average, then it would be like this formula. And then we say, so if the average is 3.8, then the probability of seeing 3 is 18.7%. But this is really, really complicated if you think about it. If we have a large system, then there are so many mesostates that correspond to this, and then we will be summing over so many factors, and it will be actually really complicated even for this simple case of multinomial factor. So what people typically do is that they use this one trick that basically is a main trick in the statistical physics, and it's the thermodynamic limit. Because what happens if we increase the number of dice? Will it get more complicated or easier? And the answer is that it gets much easier, because what we do is that if we throw 5 dice, not 5 dice, but 10 dice, but the average value is the same, then the multiplicity will look like this. So if we say we now have the mesostates where we say we start with the specific cases where we just double the sequence. So if there were 2 6s, then it's 4, etc., etc. And then this multiplicity looks like this. So this always 2 times. And now it dramatically changes the multiplicities, because now we see that while they grow, they don't grow the same. So here it's like the ratio between the highest and lowest is much larger. So basically it means that this one dominates. I have to say that there are other states that are not double configurations, but what we see is that basically it means that by increasing this size of the system, then the most probable configurations will become even more probable. So this is something that people sometimes call measure accumulating theorem, which then make our life easier, because then we don't have to consider all of these mesostates, but basically take the one that has the maximum probability. And now we see where the maximum entropy principle comes into the game, right? Because now when we rescale the system, and this is what is called thermodynamic limit, most probable mesostates are observed much more often than the rest of the mesostates. So in thermodynamics, if you are dealing with a large number of degrees of freedom, let's say a mole of dice, now if we are for some reason throwing dice again, then it means that only the mesostate with largest multiplicity becomes relevant, and all the others become negligible. And this is the reason why we can use the principle of maximum entropy and do not have to use this very complicated formula, because basically all this, if we say this is like WRI, WMI over sum over MI is the probability of observing the mesostate, then they will basically go to delta function, because they're only the most probably will survive and the rest will basically disappear. And this means that we can calculate the state with the maximum multiplicity, and this we can do by maximizing the entropy. This is the log of the multiplicity. Now, we could also do this with the multiplicity itself, but we know that from taking the log, we basically change the product to sum, which makes the calculation easier. So now, basically, it means that if we use the Boltzmann formula, then basically what we do is that we maximize the Boltzmann-Gibbs entropy. And now the question is, good, so this is what we know in statistical physics, and this is what most of the participants here use every day, right? Now the question is, okay, what happens if the multiplicity is not multinomial factor? Can we derive the entropy for these systems? And this means that basically, in this case, we are dealing with something, maybe it could be definition or observation, that in complex systems you don't have often the multinomial multiplicity, because this is connected to the fact that the trials are independent, and if there is some correlations in the system or some interactions in the system, then basically we start seeing other multiplicities than this multinomial factor. And then the interesting part, and this is the basically the core of this lecture, is to show how does the entropy look like. And we can start with something that is very well known, but maybe people are not deriving this way. And this is the Maxwell-Boltzmann, Fermi-Dirac, and Bose-Einstein statistics. And this is very interesting because especially the Fermi-Dirac and Bose-Einstein, they are very often derived from the grand canonical ensemble. But I show you that you can do the same thing with the canonical ensemble. You just have to carefully calculate the multiplicity of the system. So the first part is that if you take Maxwell-Boltzmann statistics, so you have n distinguishable particles, and you have ni particles in state E, then the multiplicity can be chosen this way. So basically what you do is that you take first the n1 particles that are in state E1, and then from the rest you take the n2 particles that are in state E2, and then from the rest, etc., etc., and then in the last you take the remaining ones that are in state nk. And then if you expand these binomial factors, what you get is that you get the n factorial over product of ni factorial. And if the EI has the degeneracy DI, where you say there are for the state I there's a possible GI microstates, then you get the same formula with just the n factorial times GI to NI over NI. And then what you can get is that you have the Maxwell-Boltzmann formula just with the degeneracies GI. This is like here. So you get it also from this multiplicity. So this is simple, but now we can plug in some other statistics. So let's say now we have Bose-Einstein statistics, where we say I have n indistinguishable particles and ni particles with state epsilon I with the degeneracy GI. Now basically what I can do is that I can calculate each binomial factor by taking the Barson-Starr formula, because then each state can have 0, 1, 2, 3, 4, etc. states. So then I'm choosing ni plus gi minus 1 over n, and you take the product. And then if we introduce this relative degeneracy, the alpha I, then the entropy for the Bose-Einstein statistics is basically this entropy. And in the second part of the lecture, I will show that this actually really leads to Bose-Einstein distribution. And this is something you would also derive if you were considering the grand canonical ensemble. It's just that now we are directly counting with this multiplicity. So it means that you can also do it in the canonical ensemble. It's just that you have this different number of states for the different degeneracies in each state. Similar thing, what you do is that if you have Fermi-Dirac statistics, you can do the same thing. Then you have the Ni particles in state epsilon I with the degeneracy Gi, but now you allow maximally one particle per sublevel. So that's why Ni must be smaller than or equal than Gi. And then basically it means that you are not choosing from here Ni plus Gi minus 1, but only Gi states. And again, you get a very similar formula to the previous one. The main difference here is that here is a plus and here is minus in this case, but here is minus and here is plus. And this whole difference then leads to this difference in the sign of the Fermi-Dirac and Boltzmann-Einstein statistics. This is what we show later. Good. So these are examples where already we get some corrections to Shannon entropy, but these are well known in physics. So maybe let's go to something that is not that well known. And these are structure forming systems. So we can continue with an example where you have simple systems. So now it's not dice, it's coins. So let's say we are tossing a coin. And now the states are head or tail, but we make a small change. We make the coins magnetic, which means that there is a third state. If the two coins stick together, they form this bound state that we simply call 1, 2. So it's a like bound state. It could have like some internal structure. We could say this is like head, tail, tail, head, whatever. But for simplicity, let's say this is this state. And this is important because this state space grows actually super exponentially, which means that the number of configurations with increasing the number of coins grows faster than sum to the size of the system. So it goes like n to n. So basically it goes like n to e to log n log n. So the log n is the correction. And this might seem like a small correction, but actually it's really in the asymptotic limit, it grows much faster. And what one can also show is that in this case, when you have non-constraints, most of the configurations are containing bound states. So you can basically estimate this by solving some recurrence equation and for the multiplicity and get the estimate on the number of possible states. And now what one can do is that one can calculate this multiplicity by doing the same thing we did before. So again, we take all the microstates and then calculate how many microstates correspond to the same mesostate. So let's say microstate is that we have head, tail, head, tail, head, 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 tail. Mesostate is basically the histogram. So 2 times we see head, once we see tail. So there's like 3 mesostates. But another microstate can be head, and then second and third coin stick together, or first and second stick together, and head and first and third stick together. So this again, multiplicity is like 3. Okay, so now how we calculate this? Again, what we do is that we take the mesostate and then do all the permutations, but then we have to count for overcounting. So here, like head, tail is here appeared twice, because if we say 1, 2, 3 and 1 and 2, 1, 3, this is basically the same state. So this is how we will correct for the overcounting. And the general formula looks like this. So we have Nij molecules. J is the size of the molecule. And we say we take all the permutations. This is the Nij. But then we also have to correct for the permutations of molecules. So this is this first factor, and then also the permutations of particles in the molecules. And basically the general formula looks like this. So this is the n over nij n factorial over the product of nij factorial. This is what we already saw in the Boltzmann formula for the Shannon entropy. There is the correction where it's the j factorial. J is the size of the molecule to nij. And interestingly enough, when we were this has been described in our paper 5 years ago. We were looking at some old papers by Boltzmann himself. Discovered is that he already was considering this type of multiplicity in 1880 paper when he was interested in studying chemical reaction. So basically, here he considers to consider a reaction between chlorine and hydrogen to create chloride hydrogen molecule. And if you look at the formula, it's basically the same as I showed you before. The reason why it was forgotten is that later people came, or it was mainly Gibbs who came with the idea of canonical ensemble, where the calculations are much easier to do, which I will show you. But if you have a system that has really a fixed number of molecules, then this is the formula that you should be using. So already Boltzmann knew this in 1884, but somehow then people kind of forgot about this. And now if we plug into this formula, then we do the same trick as before. We use the Stirling's formula, and we introduce something that I call now probabilities. The reason is that these do not sum up to 1. They sum up to 1 only if you multiply this by the size of the molecule, because each molecule is the kind of the number of molecules over the total number of particles, but it should be number of particles in the molecule over the total number of particles. And what you get is that first you get this -1. This is something you get also in Boltzmann formula, but since this sums up to 1, it's a constant that you can forget about. Here you have to keep it, but more importantly, there is the second term, is the pi times this logarithm. And this is what is the most important correction to this. And if you consider some finite interaction range, and there you can replace this with the concentration. Okay. I will show you also what is the maximum entropy distribution later when I will be doing this overview. I think it will be in the second part of the lecture. Now I have like 3 more examples. One is the so-called sample space reducing processes. This is what my colleagues Rudy, Stefan, and Bernard introduced, and it's kind of the simple version of path-dependent processes where your current state depends on the previous state. And it's very simple that you say in normal sampling, in normal physics, I say that this next state that is, for example, determined by transition rate, is just the next state can be any other state that is available. So there is no constraints on what is the next state. In a sample space reducing process, you can imagine it as a staircase where you say the next state must have lower energy than my current state. So what you do is that if you throw a dice and you have 13, and this is like dice with, I don't know, like 20 sides, then the next dice is basically smaller. It has to be 13. Then 9, 7, 5, 3, 1. And then only if you reach the ground state, then you are allowed to come back to the highest state. So you like go down, and then here is a little elevator that brings you back, because otherwise it would be trivial. Good. And if you're now starting to derive what is the multiplicity of this, then basically it's also relatively simple, because then you don't think about the states, but in the sequences of state, where you say, I have a sequence that ends in the ground state, and then I can jump up. So basically it means that there are all the sequences that contain this ground state. So basically this is this x1. and how many of these sequences contain state xj, exactly kj times, you do the same thing where you say it must be always this k1. So this is the number of runs. So it's that x1 must be in all of these runs. So this is the multiplicity formula for this. And if you look at this is like the product, and what you get is that basically the formula after some mathematics look like this: pi over pi p1 minus pi, and this is the ratio. If you look at this, it reminds a formula that we saw before, and this is the formula for the Fermi-Dirac statistics, actually, where alpha must be p1, because it's that each of these states can appear maximally once in the sequence, and the k1 appears always. So now we have another interpretation for the same formula, is that it can either describe their Fermi-Dirac statistics or this path dependent systems. Okay, one more example is Poya-Ernst. Poya-Ernst is a system where it also has this like dependence on its history, where you have an urn, and then there are some balls with some colors. And basically what you do is that if you randomly pick one ball, and if you pick the ball, you look at the color and return more balls than of the same color. So it's like here, if you say delta is 2, then basically when you draw a ball of certain color, then it's replaced by 1 plus delta balls of the same color. So it means that it's kind of, again, history-dependent dynamics, where you are adding the balls to the color and are changing the probabilities of drawing the ball of given color for the next run. And you can do, again, calculate this probability of a sequence. I will now not go to that many details, but basically it means that when you draw a ball, then you return this delta ki balls. So this is how the number of balls change. So ki is that I draw this ball ki times. And then it looks like this. We use this representation of these numbers, where m delta r is the m times m plus delta. So it's kind of like generalized factorial way, but with some terms left out. Good. And if you do that, you can see that it's, again, you can derive, you can take the logarithm, which changes to the sum, and then basically what you do is that you also have the probability of observing this histogram. You can do all the calculations. I don't want to go to the details, but basically you find that there is this formula. So it's like log pi 1 plus n. Interestingly enough, there is no pi in front of the logarithm, in contrast to the Shannon entropy, which might seem like a small change, but it's actually a huge difference, because what we see is that this leads to dynamics that is called winner takes it all. So basically, you can see that in certain cases, it leads to this situation where you have a delta function that basically, if I draw the balls in one of the first rounds, then there are more balls of that color, and then the probability is larger and larger, and at some point I will be only drawing these balls. So this is what happens in this case. Okay, one more example that people are aware maybe is that this Q deformations, is another type of entropies that is not typically derived from multiplicity, but you can make it derive from the multiplicity, but it's kind of complicated way. In order to do that, you have to define like Q exponentials and Q logarithms. So basically, if an exponential is limit of 1 plus x over n to n, you just take the finite version of this, and then you can derive also an inverse function, which is the logarithm, and then you can generalize operations like multiplication and addition, etc., so that the skew logarithms and the skew versions basically satisfy the regular extensions of the regular additivity and extensivity for exponential logarithms. So then a q times b is look like this, and then what you do is that you have to then also apply it to the factorials, and then basically you say that if there is a system that considers this q that which multiplicity is this q deformed multinomial factor, then if you do some calculations and use this generalized Stirling approximation, then you end with the what people call Thales entropy, with the with the index 2 minus q, but this is something that has been discussed. There is this relation between q and 2 minus q. But
sorry, Jan, just to mention briefly, the time is now at 46.
Yeah. I think I'm close to finish this first part. So so you see that, I mean, while this is possible, this is really complicated way to derive, and one would really have to think about a system that has this multiplicity. So that's why I don't think in this case is the most important example of a generalized entropy for complex systems. It can be useful. It's useful in certain applications, but really the derivation through the multiplicity would be very complicated. Good. And I think that I can stop here, the first part, because then in the second part, this is a little easier, that now we calculated the entropies, and you are also interested in how the MaxEnt distributions look like, and what is the consequence for the thermodynamics of these systems. And this is what I will show in the second part. Okay, so I will finish here. If you have any questions, do not hesitate to ask me. Thank you.
Thank you very much, Jan. We have a few minutes before the break. If anyone would like to ask a question, please feel free to either raise your hand or just unmute yourself and ask it.
Okay.
Ferenc, please.
Hi. Thank you very much. It was very interesting. I just wonder how you can define the Rényi entropy, which is quite often used instead of the Shannon entropy.
I don't have the slide here, but I will show you. We have a very nice paper that describes this, not through multiplicity actually. What we show is that it arises naturally if you exchange the way you calculate your averages from regular arithmetic averages to something that is called Kolmogorov-Nagumo exponential average. And this has many applications in systems like multifractals. There you naturally get the Rényi entropy. But from multiplicity, also the problem is that it doesn't have this form, because this like log W leads to something that it is like sum of something. So it is trace class of entropies, which is not really there. So from the multiplicity itself, it's really not that straightforward, I would say. But it's useful in certain applications for sure.
Okay, thank you.
Thank you very much. Reinhard, please.
So you showed us now that you can define different types of entropies.
Mm-hmm.
And what I would be interested just at the questions, if we have a physical system or we have a social system or an economic systems, could you classify, so to say, for the systems, which entropy is useful?
Mm-hmm.
I would like to understand you if you say that the social systems needs a different type of entropy as physical systems, where I have classical electrodynamics and make my measurements of specific heat, and in social systems I have to do something else. So that's my idea. What I can get from this.
This is a great question actually. So of course this whole assumption is basically relying on the fact that you can calculate the multiplicity of your system, which means that you have to know all the microstates of your system, which is possible in like simple systems or physics systems, but it's not possible in something like social systems where you don't know what a state is, what is the degree of freedom, and these things. What I will show at the end is that there are some hints that can show you, for example, like if you have some asymptotic behavior of your system that can point to a certain class of entropies that can be useful for that system. So then it's also that you don't use the Boltzmann entropy because you don't know the multiplicity, but you use some generalized entropic formula because it has some properties that you like. For example, that it scales with the size of the system somehow, or that you know that the interactions are of some kind. There, I will show some possible classifications of these entropies and where these can be useful. But unfortunately, you will not be able to derive it from Boltzmann's formula, typically.
Okay, thank you. Thank you.
Thank you very much. That's brought us to a time of 51. So as promised, let's take our break between the lectures. Let's aim to restart sharply at 4 o'clock Lviv time. I will stay on the call and just mute and de-video myself, but I'll be back a couple of minutes before the session starts.
Perfect.
Great. Thank you very much, Jan. We look forward to part 2 in 9 minutes' time.